Okay, this will be the test prep video for optimization problems. That's section 4.6. Optimization. That's where you want to minimize something or maximize something. So let me lay out, instead of doing the very general ones that are kind of easy but don't really have a lot of meaning, let's look at this example 3 first. Because this is a problem you might run into in real life. You want to say fence a garden. You've got, as where I live, lots of squirrels and bunnies and all sorts of critters, and you want to fence around the area, but you don't want to spend a lot of money fencing, but you think 75 square feet. So you want to know, how do I get 75 square feet? What shape do I need to make? What kind of a square or rectangle in order to minimize the fencing? That seems like a real life problem. So what we're going to say is find the dimensions of a rectangle of area 75 square feet that has a minimum perimeter. Okay, so that seems like a pretty straightforward problem. So let's look at what we need to do in order, when you're faced with a problem, how do you know how to start? That's always one of the hardest things. So the first thing you need to do is identify, in this case, the quantity you are trying to optimize. That is, which one are you trying to make a max or a min? So it'll be one or the other, max or min. And then go ahead and write, what units what you're trying to report. So so actually there are two pieces here. You're going to identify the quantity to optimize, but then also separately what quantities you will report. Those are separate. Let's go back and look at our problem here. I want to minimize the perimeter, but what I want to know are the dimensions. So those are really kind of two pieces. So that's one. Two, if there's a sketch you can draw that will help you, please sketch and or list everything that you know. That's good to have it anytime you look at a word problem. The next thing we're going to do is to write what I'm calling the primary, or maybe a good word would be, I'll say the primary, no, I'll say the optimum. I'll say the optimization equation. And so this pertains to whatever you're trying to optimize. So in this case, so let's just kind of go back and forth. So I need to first identify. I know that I'm trying to find minimum perimeter. And go ahead and use variables when you can, because math is about variables, and that quickly translates the English into math. So I want to know the minimum perimeter. I want to report dimensions. Okay, so let's draw a picture. We know we have a rectangle, and we normally describe rectangles as length versus width. It doesn't matter which one you call which. You can call them X and Y, A and B, it doesn't matter. And so is there anything else we know? We do know that the area in the middle is 75. Okay, so we've done 2. Number 3, write the optimization equation. That means go back up here, the thing you're trying to minimize, and write the equation for that. So you're trying to minimize, and go ahead and write the optimization again. Perimeter. What is the perimeter of a rectangle? 2W plus 2L. I make my L's that way so they don't look like 1s. Okay, so this is what we're trying to minimize. Okay, that's great, but they're 2 variables. And we can't do that in 2 variables. So that's the next thing we need to do then, is to write a secondary equation. There's more information in the problem. Write your secondary equation, and you're going to use this one for substituting out one variable. So that way we can go down from 2 variables down to 1. Okay, so what other information do I know here? I know that the area is 75. What's the area of a triangle? Width times length. So I know this. Okay, so I can use, and I know that this is equal to 75. I know all of that. So I can use, I want to keep, this is the equation I want to work with, because that's the one I'm trying to minimize, which means I'm going to take the derivative. So I need to use this to get rid of one of those variables. So the next step we'll do, as part of this step, is to solve. So we need to solve this for one of them. It really doesn't matter which one. I kind of prefer to work with W's than L's, so I'm going to write this as L equals 75 over W. And now you use this to substitute in your optimization equation so that you can get down to one variable. So now what do I have? I'm ready to work some calculus, so I have perimeter is equal to 2W plus 2 times 75 over W. Let's go ahead and clean that up. 2W plus 150 over W. Okay, so now I'm ready for the derivative, because the whole point is to minimize this, so I need to find if there's a minimum. So P prime. So here we're at the calculus step. And we'll use that to find either the max or min. And then our final step will be to answer the question and to make sure that it makes sense. Okay, so let's take the derivative. Derivative of 2W is 2. I'm going to rewrite this one as 150 W to the minus 1, then it's a simple power, minus 150 W to the minus 2. Now this is one where eventually we're going to set this equal to 0. We need to rewrite this as a fraction, a rational expression with a denominator, and then combine into one rational expression first. So this will be 2 minus 150 over W squared. Okay, so what is the common denominator here? This is like 2 over 1, so W squared. So then this would be finally 2W squared minus 150 divided by W squared. That's what we need to work our sign chart magic on. So we know the denominator is 0. Gives us 0 for a partition point. So what about this one? Well, let's just keep working. W squared minus 75. Some of you will see quickly that the answer to this will be plus or minus square root of 75. And we get that just from setting that equal. 75, that can be simplified. I can pull 25 out, so this will be plus or minus 25 root 3. Okay, so let's get all that on here. 25 root 3, negative 25 root 3. But now we need to pause for a minute. We need to be sensible about this and think about real life. Is it possible to have, remember this is a width, a distance, that's negative? No. In fact, any of these values right here, all of this is gone. So it's important to pay attention to your domain when you're doing a sign chart, because there are a lot of times where a whole piece of it won't be necessary, won't exist. Okay, so let's put in some numbers. I'm thinking 1. I put in 1 here, I clearly get a negative number. So that's negative. And I put in, I don't know, 100. That'll clearly be positive. So this goes down and then up. So do we have a min? Yes, we do, right here. So oh, and I made a mistake. This is, when I pull the 25 out of the square root, it is 5 square root of 3, not 25 square root of 3. So this tells me then that I have a min at W, my width, equals 5 square root of 3. Okay, so am I done? Have I answered the question? I am supposed to find and report the dimensions plural, so width and length. So let's go and find our last one. I'm thinking we can use this form right here. And so we're good. Length equals 75 over, and I'm going to go back to this form, 75 over square root 75, because then that seems a little bit more apparent to me that that's 75. Square root of 75. So then our final answer, width times length, would be 5 root 3 for the width and the same for the length. Okay, so that's a good example for the first one. So again, let's review what we did. The first thing we want to do after we read the problem is figure out what we're trying to minimize, write that down. And then figure out what we need to report as an answer. And then let's start writing everything else we know. Any sort of geometry we know, any other information we know, write that all down. Okay, so now that's everything we know and are trying to find. Those are always the first steps in a word problem. Then come back to your optimization equation and actually write what it is. So 2w plus 2l. Two variables, that's a problem. We need to write more information, which we have, solve for one variable, and plug that back in. Once we've done that, now we have something in just one variable. So we can take the derivative, clean it up. It's important here, when we're trying to find the values for the sign chart, to get all the way to this point. In order to set this equal to 0, we have to have one numerator and one denominator, so just one fraction. Okay, so we go ahead and pay attention to our domain, get our sign chart, figure out if we have answered our question. We have, we do have them in there, and then go back in to this secondary equation and find out the rest of the information. Okay, so that's one. All right, so now let's come back and look at some examples that are in some sense a little easier, but also have less context. So sometimes they're difficult just because they don't seem to really mean anything, or at least nothing of importance. Okay, so here's one. Find two numbers whose sum is 21 and product is maximum. Okay, so first question. How do I know that this is an optimization problem? Well, I do because I see the word maximum. I'm trying to find where something is a maximum or a minimum. That's a key word. So the first thing I need to do is write down what am I trying to maximize? P, the product. And what am I trying to find? Two numbers. Let's just call them X and Y, A and B. It really doesn't matter. Okay. Is there anything to sketch? No. Do we have any extra information? In fact, let's write that over here. Yes, we do know that the sum, X plus Y, is 21. Okay, so we do have a little extra information. So now we're going to go back to what we're trying to maximize. We're trying to maximize P, the product. That means X times Y. Again, two variables. We can't have that. So we'll come back over here well, I guess that's my secondary equation. That's part of what I knew. So this is actually, in this case, also step 4, the secondary equation. Now I'm going to solve it. So let's just say Y equals 21 minus X. I'm going to take this and put it in here for Y. So now we have P equals X times 21 minus X. All right, multiply it out just because I really don't want to do a product rule. And so now I'm ready to maximize this. So we are ready for our calculus step, our derivative. Very easy. 21 minus 2x. Okay, so we're going to set that equal to 0. When we do the division, 2x equals 21, we'll get 10.5. It did not say anything about the number, so really my number line goes on forever. It doesn't, I don't have any domain issues. So let's try 1 and 20. 1, 21 minus 2, definitely positive, and 20, 21 minus 40, definitely negative. So this is going up and then coming down. So I'm looking to maximize the product, so I have my answer. So I know then that X is equal to 10.5. Is that my final answer? I needed to report two numbers. So I need to go back over here. This one that you solve for the substitution is the best one to go back in to find your other value. So 21 minus 10.5, 10.5 again. So really I have X equals 10.5 and Y equals 10.5. So again, same process. What are you trying to maximize? What are you trying to report? Write that equation, write your secondary equation, solve that so you can substitute, get rid of one variable, derivative, sign chart, answer, complete answer. Okay, one more, just because I know you guys love word problems. I just wanted to make sure to show you several different varieties. We will do some additional varieties in class that are a little bit tougher. All right, so here is the last one. This is example 2. Going out of order a little bit from the notes. Find 2 positive numbers whose product is 25 and whose sum is minimum. Okay, so step 1. What are we trying to do? We are trying to minimize the sum. And what are we trying to find? 2 positive numbers. So we're looking to find, to report x and y, but we know a little bit here. So over here in our this is our find set. Here's our known set. We know that x and y are both greater than 0. What else do we know? The product is 25. The product, x times y, is 25. Okay, so let's come back over here. So we've got our find and our known, I guess I should say. All right, so now let's come back and we are trying to minimize the sum. So the sum is x plus y. Again, 2 variables. So we're going to come over here to our secondary equation and solve for one of them. Y equals 25 over x. Could you say x equals 25 over y? Absolutely. It just means that you will get a y answer first and go back over here to get x. It really doesn't matter. So now I'm going to substitute that in. So I have x plus 25 over x.